And now we will listen to the second paper submitted by a team one, but they already nominate Dr. El-Sayeda from the National Research and Cairo region.
There is no question. There is no question.
After we will end the 5 speakers, we have 5 or more or 10 minutes to any question you will want. So we will now Dr. Hussam will present his presentation. And Dr. Hussam has his bachelor degree from Cairo University at 1990, and also his master degree from textile chemistry, Cairo University on 1996, and his PhD degree from textile chemistry of the German Institute at 2000. And he is now a researcher at World Research Institute, Asian, Germany. Please, Dr. Hussam.
Thank you, Chairman. Good afternoon, everybody. Our article today is about an enzyme for polymer-assisted shrink-resist treatment of wool. Next, please. The wool fiber can be classified as one of the luxurious fibers. Wool fiber can be classified as one of the luxurious fibers, but it suffers from 2 major drawbacks, which is wool is attacked by some insects, like moths or carpet beetles. The other drawback is wool shrinks during the mechanical agitation, during industrial processes, or any domestic laundry machine or laundry wash. Next, please. This figure shows a scanning electron micrograph of marine wool fiber from Australia. This micrograph shows the scaly structure of wool fiber, which is the main reason of the felting of wool during any mechanical agitation or mechanical processes. This scaly structure should be removed for any processes intending to felt proofing of wool. Next, please. There are conventional shrink-proofing processes used in felt-proofing of wool in industry. Wool is rendered shrink-proofed by one of 2 methods. Degradative processes, this is by oxidation using oxidizing agent to remove part of the scales of wool. And the other method is additive processes. This is performed by resin application or polymer application. The third new method is a combination between the 2 conventional methods, which is combination of degradative and additive process. I mean, the first step is oxidation of wool and to modify the wool surface to be compatible to the polymer or the resin applied in the second step, which is additive process. The state of the art in wool felt-proofing industry. Today, the most commercially successful process for producing machine washable wool, I mean felt-proof wool or shrink-proof wool top, is the IWS International Wool Secretariat Cyro-Chlorine Hercosset process. This process was invented in, I guess, 1971, and until now it is the most successful one. But the use of chlorine as a fiber modifying agent produces environmentally unfriendly adsorbable organohalogen compounds. So the use of chlorine for this purpose became undesirable from the ecological point of view. Next, please. And now the aim of the work. The present investigation aims to study an ecologically acceptable non-chlorine shrink process of wool based on catalytic hydrogen peroxide oxidation treatment. This is to modify the whole surface. Followed by protease after treatment. Followed by, we can say, 3 different after treatment steps or processes. Protease after treatment. This is by using certain type of protease enzymes, or by polymer application. And we have used 2 different extremes of polymers, ketosane as a natural polymer, and hercosette 617 as a synthetic one. So the work again is oxidative treatment of wool by hydrogen peroxide to modify the surface of wool to be compatible with many different after treatment processes using either protease after treatment or polymer application. And the polymer used maybe biopolymer like ketosane or synthetic polymer like hercosette 617. And in our work, in the experimental study, we have oxidized wool tops by hydrogen peroxide via pre-treatment with 0.5 to 10 milligram copper sulfate pentahydrate. We have chosen this concentration in order to be in the allowed limit of copper in the wastewater, or the allowed limit of copper which can be extracted during wearing from sweat or anything like that. So the first step is pre-metallization of wool tops using very low concentration of copper sulfate, then oxidation of wool by hydrogen peroxide and sulfatolysis. Oxidation of wool will oxidize the disulphide bond or modify the disulphide bond of wool, and sulfatolysis will break the disulphide bond of wool. These both processes will make wool now easy to be combined with the after treatment reagents. So the oxidized wool tops were then after treated with the proteolytic enzyme papain, or natural polymer ketosane, or the synthetic polymer hercosette 617. The resistance of wool to felting resistance was assessed according to the International Wool Textile Organization 2069 test method using the Athener 3-dimensional shaking machine. From this test, we have taken the feltable density. This test is achieved by shaking the wool sample 1 gram in 3-dimensional to get a ball. And from we measure the diameter of the ball and get the density of the felt ball. And as the density of the felt ball increases, the felting resistance becomes worse. As the felting resistance decreases, the felt ball density increases. The effect of these treatments on the mechanical properties like tenacity, elongation at break, as well as the effect on the solubility in alkali or irreversible sulfide solution were monitored using the non-standard methods. Next, please. In table 1, we have just chosen some of our data to show that the treatment of wool with hydrogen peroxide sodium sulfide without pre-metallization with metal ion like copper shows no significant improvement in the felting resistance of wool. For example, we have treated wool by hydrogen peroxide at pH 8 or hydrogen peroxide at pH 9, and we measure the felt ball density, which is the measure of the felting resistance. The felt ball density of untreated wool is 0.189, and there is no sharp decrease in the felt ball density of wool after treatment with hydrogen peroxide, and this means that there is no increase in the felting resistance. The tenacity, of course, and weight loss maybe is not affected. We can say it's not affected. So now we should use a catalyst like copper sulfate as a pre-metallization or as a pre-treatment step to enhance the oxidation of wool with hydrogen peroxide. Next, please. But the legislation in many countries, especially in Europe, should force us to study or to determine the amount of copper on the wool fiber after treatment. And the amount of copper, I mean the amount of copper which may be extracted from the sweat during wear. The upper limit is from 40 to 50 ppm for each kilogram. So we have used copper sulfate in the treatment bus, the concentration from 0.5 to 10 milligram per liter, and this can be calculated as copper element only and not as copper salt from 0.13 to 2.6 ppm. And we have calculated a lot of things, and finally we arrived at the amount of copper taken by wool is from 2.97 till 55.87, and this is within the allowed limit. Again, 55.87 is the amount of wool taken on, the amount of cover taken on wool. And it doesn't mean that the amount of cover which can be eluted from the sweat of human being is 55, maybe 10 or 20, which is under the allowed limit of cover in the wastewater or to be adhered to the skin of the living organisms. Next, please. And here we have made treatment of wool with cover as a pre-metallizing agent, then hydrogen peroxide, then sodium sulfide. We have chosen again filtrable density as a measure of the filtering resistance. Untreated wool is 0.189, hydrogen peroxide treated wool only 0.156, but cover iron and then hydrogen peroxide treatment reduces the filtrable density to about 0.05. By the way, the standard value of the IWS International Wool Secretariat is 0.039 or 0.04. So we are more or less near the standard value of the IWS. After sulfatolysis, I mean cover iron and then hydrogen peroxide and then sulfatolysis, we reaches much more nice value, which is 0.043, near the standard value of IWS. The tenacity, we can say there is no adverse effect on the tenacity of wool. Next, please. In this table, we have treated wool fiber with cover iron, then hydrogen peroxide, sodium sulfide as a previous table, and then after treatment with papain. Papain is a proteolytic enzyme which can affect the proteinic fibers only. All this value has been shown before. The new value is treatment of wool with cover, hydrogen peroxide, sodium sulfide, and then papain using 0.2% on the weight of the fiber. As we show, the filtrable density decreases to a very low value, 0.039. This is below the standard value of IWS. And we have reached also the deformed ball. The deformed ball means that when we apply the shrinkage test using the Athena three-dimensional test, the wool fiber doesn't form a ball. And this means that the wool fiber, when it is washed in laundry, in domestic laundry washing machine, it will not filter at all. If we increase the concentration of papain to 0.4% on the weight of the fiber instead of 0.2% on the weight of the fiber, we may reach the deformed ball level using 7 milligram per liter copper sulfate pentahydrate instead of 10 milligram per liter. Upon using 0.2% on the weight of the fiber papain. Unfortunately, this increase in the filtering resistance of wool is accompanied by decrease in the tenacity of wool to about 11.1 compared with more than 15 or 16 of the untreated wool fiber. Next, please. The next table will explain the use of Hercocet instead of papain in the after treatment step. And this table shows that treatment of wool with cover hydrogen peroxide, sodium sulfate, Hercocet decreases the filtrable density till 0.038, which is much less than the allowed value of the IWS. The tenacity of wool shows little decrease in the untreated wool compared with the treated one. And this is one of the advantages of this process, I mean the after treatment with Hercocet over the last one, which is after treatment with papain. Also, the weight loss is another positive sign. There is increase in weight, and this is very important for the industrialist. This is to the opposite of the last process, which shows decrease in the weight of wool fiber after treatment with papain. Next, please. Ketozan. Ketozan is used in this table instead of the proteolytic enzyme papain or the Hercocet polymer, synthetic polymer. We have chosen two ketozan models. The first one was molecular weight 1500, which is classified as low molecular weight ketozan. The second one is 30,000 ketozan, and this is classified as moderate molecular weight of ketozan. And I think there is no, I'm saying it's clear that there is no improvement in the filtering resistance of wool as The filter pole density of hydrogen peroxide sodium sulfide treatment is 0.0343, and after ketosane treatment it's only 0.041 or 0.042. I guess it is within the experimental error. So, use of ketosane by the method we have used in here, which I mean at very low temperature or at room temperature and for a short time, does it ensure the complete cross-linking between wool and the ketosane? And I guess there is no ketosane taken up on wool, or if it's taken up, it would be physical adherence which may be removed during washing. So there is no actual improvement in the filtering resistance of wool, and this is in contrast to the work of many researchers all over the world. Next, please. This photo shows the scanning electron micrograph of untreated wool fiber, and this shows the scale structure intact. Next, please. The next one is scanning electron micrograph of papain after treated wool sample, and this shows that there is a partial removal of the scale structure of wool, which ensures the filtering resistance of wool as a result of removing this scale structure, or we can say the tips of the scales of wool. Next, please. This is an academic investigation in which the solubility of wool in alkali and in urea bisulfide was studied to assess the mechanism of the reaction. For example, alkali solubility is a measure of the modification of the disulphide bond. Urea bisulfide solubility is the measure of the breaking of hydrogen bonds or formation of any new cross links. Alkali solubility shows increase. It's 14.9 for untreated wool and reaches in some cases near 50 for hydrogen peroxide sodium sulfide papain treated wool. And this means that there is a great modification on the structure of wool, especially at the disulfide bond. On the other hand, the urea bisulfide solubility shows no change, no adverse change, and this means that there is no cross links formed during this reaction with wool, and of course we can expect that. Next, please.
Dr. Said, have only 15 minutes.
So the rest is about how many seconds?
2 minutes.
Okay. Conclusion: the catalytic oxidation of wool by copper ion hydrogen peroxide sodium sulfide modifies the surface of wool and hence increases its filter resistance. Only by using copper hydrogen peroxide sodium sulfide. But by using this system, we didn't reach the standards of the International Wool Secretariat. Post-application of wool with the proteolytic enzyme papain or the synthetic cationic resin hercosette give an additional increase in this property. As we see before, we reached the deformed pole. It means the wool after domestic washing will not filter at all. The level of filtering resistance achieved by the after treatment of the oxidized wool top with papain is somewhat higher than that obtained by after treatment with hercosette. Hercosette as a cationic polymer has a certain affinity to hydrogen peroxide oxidized wool in the same manner as the case of chlorinated wool. As we said before, the usual process is chlorination and then hercosette application. The copper hydrogen peroxide sodium sulfide treated wool is capable of exhausting more than 2% of hercosette, indicating that this system, I mean copper hydrogen peroxide sodium sulfide hercosette, can be a substitute for the chlorine hercosette system if developed. Mechanical property: alkali solubility urea bisulfide solubility of wool treated with system, I mean in which hercosette is used in the after treatment step, is better than that after treated with papain. Why? The change in weight is a positive sign for the former method, for the hercosette method, and a drawback for the latter one. After treatment of the oxidized wool with the biopolymer ketosane, by the methods we have used in our investigation, has practically no improvement on its filtering resistance. We mean no chemical or physical bonding of ketosane to wool takes place. Next, please. Thanks for interest.
Thank you, Dr. Sayed, for your presentation.